Hello, my name is Mary Ford. I'm a PI in the Orogen project, and today I'm going to present a talk entitled Basins and Orogens, Insights from Pyrenean Foreland Systems. This talk integrates the work of many colleagues who are listed here, who are mainly from the Orogen project, but also come from the Source to Sink, RGF Pyrenees and Pyramid teams. Basins in collisional orogens can be grouped into four types: inherited basins that are integrated into the orogen, shown in purple here; synorogenic basins in the near field, which are the flexural foreland basins in the pro-wedge and the retro-wedge; synorogenic interplate basins that are in the far field on both plates; and finally post-orogenic basins that are not represented here. We are going to talk about the synorogenic near field basins. A flexural basin is created by the elastic response of a plate principally to the orogenic load, which evolves and migrates with time. The elastic response of the plate to loading is strongly controlled by its thermal and mechanical properties. In addition, mass transfer between the basin and orogen is controlled by the interplay of tectonic processes and surface processes linked to climate, as shown in this cartoon here. A foreland basin is therefore strongly coupled to the adjacent thrust wedge, and both make an integrated foreland system. This orogen shown here has two foreland systems, one in the pro-wedge and one in the retro-wedge. By studying natural foreland systems, we can identify and quantify orogenic processes in time and space, their interplay and interdependence, identify and track the role of controlling parameters, compare and integrate signals in diverse datasets with different spatial and temporal resolutions, and finally develop and test generic models for basin and orogen development. We are going to work on the Pyrenees as our case study, and I'm going to give you a quick introduction to this orogen before dealing with its foreland systems. The Pyrenean orogen is a world-class case study for collisional orogens. They have been studied for over 150 years. The full orogen is about 3,000 kilometers long, stretching from the North Iberian margin through the Cantabrian Mountains, through the Pyrenees, Sensu Stricto, and across into the Pyrenean Provençal belt. The orogen is particularly well known for the high quality of the outcrops, particularly in the southern Pyrenees, as shown here. To summarize the geological architecture of the Pyrenean orogen, we can say that it is a small double wedge collisional orogen with a low total north-south convergence of 90 to 135 kilometers. The pro-wedge in the Iberian plate consists of the axial zone, the South Pyrenean zone, and the Ebro Basin, with no internal metamorphic zone. The retro-wedge to the north consists of the North Pyrenean zone and the Aquitaine Basin. This North Pyrenean zone preserves the inverted Aptian to Cenomanian rift, which includes exhumed mantle peridotite and high-temperature syn-rift metamorphism, shown on the cross-section here. The north-south convergence between the Iberian and European plates is reconstructed here by Machiavelli et al. Using isochrone mapping of the South Atlantic, the southern North Atlantic, and this model is used in our reconstructions. There are three phases: an early phase during the late Cretaceous with slow convergence of around 1 millimeter a year, a quiet phase during the Paleocene, and rapid convergence of 2.5 millimeters a year during Eocene-Oligocene, and into the early Miocene, ending at about 20 million years. The Orogen project includes many studies of the Pyrenean foreland systems, and I've listed here the postdoctoral researchers and PhD researchers who have worked in these areas, and in dark blue are the ones that I've integrated into this talk. The talk is divided into three chapters. The first one is on foreland systems, and here we focus on the questions: what are basin dynamics, what is the style, amount, distribution and timing of deformation, what are the controlling parameters, and we want to try and understand better the coupling between pro-wedge and retro-wedge. On the map on the left, we see that the Aquitaine Basin is open to the Bay of Biscay and always has been throughout its history. In contrast, the Ebro Basin was initially open to the west, but is now enclosed between the Pyrenean Mountains, the Catalan coastal ranges, and the Iberian ranges. On the right, we see the isopachs for the Campanian to Miocene infill of the two Foreland basins. The Aquitaine Basin is strongly asymmetrical, thickening to over 5 kilometres just north of the thrust front. The western part is rich in salt, with many salt ridges shown here in dots. The Ebro Basin is a complex basin with up to between 4 and 5 kilometres of infill, preserved in piggyback basins on this salt-rich wedge top. I'm going to focus first on the retro basin by summarising the main characteristics using these 4 cross sections in the eastern and central Aquitaine system. To the west of the Toulouse fault, which is shown here, and between cross sections 4 and 5, the basin is superimposed on a salt-rich rift, which you see in section 5 here, while to the east the Foreland Basin onlaps directly onto Variscan basement. The retrothrust belt, the North Pyrenean zone, shown here in the south on all sections, is 12 to 30 kilometres wide and is characterised by thick-skinned inversion of the Apto-Cenomanian rift system, with a decoupling salt layer here in the Triassic. Total shortening is between 18 and 31 kilometres. The Foreland Basin records 2 shallowing up cycles with a northward migration between the upper Cretaceous depocentas shown in green here and the Eocene-Oligocene depocentas shown in orange. We can see that the thickness of the Foreland Basin thins towards the east, and this is not only due to erosion but to decrease in flexure of the basin towards the east, indicating that the orogenic load and therefore crustal thickening decreased towards the east. Here we have a summary of subsidence in 10 boreholes in the eastern and central Aquitaine system, and we see that the subsidence history can be divided into 3 phases: an early phase of slow subsidence, a quiet phase during the Paleocene, and a continuation of slow subsidence during the Eocene and through into the Oligocene. So 3 clear phases defined here. To compare the north and south sides of the orogen, I here use the work of Arjan Groul et al. 2018 of the Pyramid Project. We have 2 cross sections that are opposite each other. In the north, the section here records 18.3 kilometres of north-south shortening, or 20% of total shortening. The southern section from Jaume Burgess' work in 1993 records 92.2 kilometres of shortening, or 80% of total shortening. This is fairly consistent along the whole orogen. The distribution of deformation changes across the orogen through time, as shown here. We have got in the early phases during the late Cretaceous a distributed deformation which inverts faults, rift faults, principally in the retro wedge, but some in the pro wedge. The quiet phase is very poorly defined, but in the main Eocene-Oligocene collisional phase, the deformation focuses into the pro wedge to the south, with a clear migration of the deformation front southwards with time. So the deformation also shows a 2-phase orogenic history, with a late Cretaceous closure of the exhumed mantle domains and diffuse deformation on both margins, with reactivation of rift faults. During the main collision in the Eocene-Oligocene, the deformation focuses into the pro wedge, but gentle deformation continues in the retro wedge. Finally, here we can see the evolution of the shortening rates with time. Time is represented by the proxy cumulative shortening here along the Groul et al. Section, and we can see very low shortening rates equal on both sides of the orogen during the early phase of orogenesis, and acceleration focusing into the pro wedge with shortening rates up to 4 millimeters a year here. When we compare the subsidence on both sides of the orogen, we have already seen the retro wedge subsidence characteristics with 2 clear phases, a complete history through orogenesis, and these 2 phases of slow subsidence separated by a quiet phase. In contrast, in the pro wedge, in the Ebro Basin, we have some record of early subsidence during the late Cretaceous. The quiet phase is poorly defined, and the main subsidence is migrating southwards with time and is much faster than in the retrowedge. Pinch-up migration describes the outward migration of the basin margin onto the forebulge and is used as a proxy for migration of the orogenic load. Sinclair compared pinch-up migration in the pro and retro wedges, linking their contrasting signatures to the evolution of orogen topography from a growth phase here to a steady state phase here. In this cartoon on the right, chronostratigraphy is represented for the pro and retro wedge Foreland basins. The vertical scale is time. During the growth phase, we have outward migration on both sides. It's fairly symmetrical. And then when we get into a steady state, the loading is focused in onto the pro wedge, and we have a rapid migration, pinch-up migration onto the foreland. In contrast, in the retro wedge, the basin becomes static and accumulates a condensed succession. How does this compare with the Pyrenean foreland systems? In the southern Ebro Basin, we see that the pattern of pinch-out shown in blue here fits pretty well with this model, with a marked acceleration during the main collision phase. In contrast, in the eastern and central Aquitaine Basin, we see here the pinch-up migration on 6 cross-sections, and they all show a fairly consistent outward migration at 2 millimeters a year, so fairly slow, with a marked perturbation during the quiet phase here during the Paleocene. Clearly, the growth of the orogen topography does not adequately explain the retroforeland basin behavior, and we'll come back to this point later. The role of salt has become a major focus in research, including within the Orogen project. The principal evaporite horizon is the pre-rift to early syn-rift Kuiper succession of Upper Triassic age. As shown in this recent compilation of studies in and around the Pyrenees, halokinetic signatures are being documented through the alpine cycle from early salt mobilization in the Jurassic, passive diaperism during the Aptian, Albian, Cenomanian rifting, and diaper reactivation during the collisional phases. During rifting and compression, the Kuiper frequently acts as a decoupling level, as shown in these cross-sections, between the deforming basement and the deforming Mesozoic cover. Very detailed mapping work is documenting typical halokinetic stratal architectures in Jurassic and early Cretaceous depot centers, as well as in synorogenic basins, where it is often difficult to separate shortening and halokinetic records. To show you some examples here, this is the work of Laure Bourrel in the southern Pyrenees, where she suggests that many of the synclines may be tightened mini-basins. In the northeast Pyrenees and Corbière, Antoine Cramades is mapping an inverted salt-rich margin with Jurassic detached faults, as shown here. In the Calabrian ranges, Jordi Miro has been working on comparing his field data to analog modelling to understand the difference between coupling and decoupling inversion. And I've worked myself in the Northeast Pyrenees on salt structures, identifying them as rift-related. So now we come back to the question, what are the geodynamic processes that contribute to the evolution of the retro and pro-Foreland Basin systems in the Pyrenees? And of course, the main controlling factor is plate convergence. And it is interesting here to compare the kinematic movement of the plates. This is the north-south convergence calculated by Machiavelli for the Eastern Pyrenees, shown in green. And we compare it here with the shortening distribution through time calculated by Ariane Grohl on his cross-section through the Eastern Pyrenees. And we see that they are very similar, with low shortening or convergence in the late Cretaceous, a quiet phase which doesn't exactly correspond, and this main convergence in the Eocene and Oligocene. So we can say that the plate kinematics can be related directly to the timing and amount of total shortening, to the shortening rates, to the retro-wedge pinch-out migration and subsidence phases, and this means that this is a very reactive orogen. We've already discussed that the topographic load has a direct impact on the pro-wedge Foreland basin, but it cannot account for Foreland basin behavior in the retro-wedge. And this requires us to look in more detail at the retro-wedge Foreland basin. And I show you here the work of Paul Engrand, who did his PhD in the RGF Pyrenees project. Here, Paul is mapping out the rift, Abto-Albian rifts that lie below the western Aquitaine basin. And you can see the beta factors here with maximum thinning here in the west of the area. From this, he can derive how much thermal subsidence, post-rift thermal subsidence occurred during the orogen, and we can see here a representation of thermal subsidence during orogenesis in the Aquitaine Foreland basin. And essentially what you see is that it's most important in the west, and on the western profile, the observed subsidence, which is shown by this blue line, can be fully explained by post-rift thermal subsidence. In contrast, in the central basin on the central profile, the observed flexural subsidence that we see requires contributions from hidden lows, topographic loads, and thermal subsidence. So we have considered three major geodynamic processes that can explain most of the observations that we've made in our basins and thrust belts. However, none of these factors can explain the changing distribution of deformation between the pro and retro wedges during convergence. To summarize this first chapter, we can say that there are two main phases in basin history and deformation. The pro and retro wedges are dynamically linked throughout their evolution. The style of shortening in both pro and retro wedges is controlled by inherited mechanical stratigraphy, in particular the presence of salt. The retro wedge is also strongly influenced by the inherited rifted crustal structure. The timing and amount of shortening can be directly linked to plate kinematics, and this means that this is a highly reactive orogen. The pro-Foreland basin dynamics can be linked to the growth of the orogenic topography, but in contrast, we cannot detect steady-state signal in the retro wedge. This is mainly because the retro wedge is very strongly controlled by the thermal substance which it has inherited from rifting. So we come back to this question: what controls the changing distribution of deformation across the pro and retro Foreland systems? And for this, we're going to look at early convergence and the transition to main collision. So to start with, I'm going to show you these paleogeographic maps based on the Machiavelli reconstructions and constructed by Gianluca Frasca in his postdoc. I'm going to ask you to focus on the Pyrenean trough here, which is a continuous basin that covers the whole of the early convergence zone. So we have crustal thickening going on underneath this marine basin, which opens to the west. So there is little or no relief in the Pyrenees. This basin is fed in from the east and from the Massif Central. We have very low, slow shortening distributed on reactivated faults, as we saw before. One of the questions in this early orogenesis is whether we can pick up thermal cooling during this phase, and this was the task of Sébastien Ternois in his thesis. He worked on the Agli Massif in the eastern Pyrenees, and he applied in situ zircon, uranium, thorium, helium dating to these basement rocks. He detected an early cooling dated at around 75 million years, and he modeled this with various scenarios and was able to show that we definitely had a cooling phase during the late Cretaceous. However, as we saw, there's no topography in this in the orogen at this time. So the orogenic cooling cannot be related to uplift and erosion. So instead, Sebastian has constructed this model in which the cooling, which occurs at this phase here of the Agli Massif shown in A, is due to the packaging of this basement massif between cooler blocks which come from Europe and Iberia. This is an ongoing project, and we have the detection of early cooling in detrital zircons being developed by using double dating of these zircons using uranium, thorium, helium and uranium lead, which is being developed at the CRPG, started by Sébastien Ternois, and the work is ongoing with Julien Léger. When we go further and dezoom a bit from the Pyrenean orogen itself, we can look at the broader European plate. And here I present you the work of Armin Dilforder in his postdoc. Armin made the key observation that the phases that we detect in the Pyrenees during early convergence show very close similarities to what is documented in the Central European Basin system about 1,000 kilometers to the north. So in both these basins, which are shown here, North Pyrenean Foreland Basin and Central European Basins, we see an early convergence phase in the late Cretaceous. We see a stasis or quiet phase in both basins during the Paleocene. And remarkably, the North Pyrenean system reactivates during the main collision, but we do not see a reactivation in Central Europe. So Armin asked the question, why is it that in the late Cretaceous we can transmit stresses from the Pyrenean orogen through to the Central European basins to invert them, but that it appears in the main collision phase we no longer are transmitting sufficient stress to invert these basins any further? This is shown in this cartoon here. This is the transmission of stress necessary to invert these basins in the early phase, in the onset of collision. And he proposes that this is related to the gradual evolution and development of a plate margin fault that accommodated the subduction of the Iberian plate during main collision. So in this early phase, we have got strong lithospheric contact between the two plates, and we can transmit stress. So a strong plate coupling here. As we develop the convergence, this plate margin fault becomes weaker and more efficient, and this reduces the mechanical coupling between the plates, and less stress is transmitted into the European plate. And this is the main collision where all the deformation is focusing into the orogen. So Armin's work can explain the two phases of distribution of deformation with time. And another work that also provides an explanation for this two-phase evolution of deformation is that of Arjan Groll and his thermomechanical modeling, which he did with Ritzke Huisman. This is his model here, and it incorporates an inherited rift and 1 kilometer of weak viscous salt at the base of the pre-orogenic sediments. And it also incorporates efficient surface processes. What we can see in this evolution is that rift inheritance promotes a two-phase shortening distribution with an early symmetrical distribution, which is expressed by the inversion of rift structures, the establishment of an asymmetrical efficient subduction, and the formation of this doubly vergent orogen. When combined with efficient surface processes, the salt décollement also plays a very important role in that it ensures that the inner thick-skinned pro-wedge taper, which is the basement axial zone here, remains subcritical and thus promotes the formation of an antiformal stack. In summary of this second chapter on early convergence and transition to main collision, we can say that we have detected early orogenic cooling using low temperature thermochronology. And we have explained that this cooling is due to crustal thickening below an early Foreland basin rather than due to uplift and erosion. We've shown that we have synchronous far-field and near-field basin dynamics during early convergence because stress can be transmitted across a strong plate contact at this stage. However, during main collision, deformation and basin development becomes focused into the origin and onto a weak plate boundary fault. We've seen also that a pre-existing rift is essential for the development of a doubly vergent origin and its Foreland basins, and that salt plays a major role in the dynamics of these origins at a crustal scale. Finally, we come back to the question we asked at the beginning of the chapter. We can say that the changing distribution of deformation in two phases of origin growth can be linked to the formation of a new plate boundary that generates asymmetrical subduction of the lower plate. The final chapter of this talk is entitled Sediment Routing Systems, Stratigraphy and Sedimentation Patterns, where we ask the questions: how do sediment routing systems evolve during orogenesis? What are the main controlling parameters? How do sedimentation patterns record major transitions between phases of orogenesis? And how do we improve stratigraphic resolution? I'll come back here to the paleogeographic reconstructions of Janaluca Frasca, and I show you here again the Campanian paleogeography, which shows the Pyrenean trough as a single broad flexural basin covering the zone of early convergence, with sediment supply coming in from the east. There was little or no orogenic relief either in the Pyrenees or in the Alps at this stage. This single basin geometry continued in the quiet phase, but you can see here that we start getting orogenic relief in the east, and the continental to marine facies belts are migrating westward with time because the construction of orogenic relief is diachronous, growing from east to west. The sediment supply is still coming in from the east, also from the Catalan coastal ranges and from the Massif Central. In the main collisional phase, this is in the middle Eocene, the orogenic belt has now created its relief, and it is supplying sediment both to the southern Ebro Basin and to the northern Aquitaine Basin. Both these basins are open to the west, with marine conditions coming right into the east in the southern Pyrenees. Now, a question here is, how do we detect this passage from early convergence to main convergence in different data sets? The reconstructions that I've just shown you are based on sedimentology, basin fill structure, and it shows that the signal in the basin of main collision starts in the early Eocene. However, when we look at the thermochronology data, which is shown here from Bernard 2019, we see that the exhumation or cooling rates here mark an acceleration which is diachronous and starts at about 45 million years, which is in the middle of the Eocene, and migrates southwards with time. So we have an asymmetrical growth of relief with time from north to south. And as I've said, there's also a diachronous growth of relief from west to east. The modeling there's been some modeling of these thermochronological data which indicate, for example, here in Maggie Curry's work, that the maximum growth of topography was at the end of the Eocene. So all these different data sets are telling us different things and at different resolutions about the growth of relief and the evolution of sediment supply. And we have to be careful when comparing these different data sets. If we carry on with our the evolution of relief, this is towards the end of the of the Eocene. So this is the height of collision, if you like. We have our maximum topography coming up in here, and we have the sediment supply to the north and to the south. And you can see that the Ebro Basin is now enclosed while the Aquitaine Basin remains open. The Chattian is the end of orogenesis, and you can see the relief is still supplying sediment into the endorheic Ebro Basin, the Aquitaine Basin remaining open. And we pass now into the post-drift phase. And we ask the question here about what is the stratigraphic or sedimentological signature of this transition from syn to post-orogenesis? This was a question asked by Thomas Bernard in his thesis, and he worked on the North Pyrenean frontal thrust and Foreland Basin here. In the Pyrenees, as you've seen, the thermochronological data indicate that convergence ended at about 23 million years. However, the sedimentation continued in the Foreland Basin for about 10 million years after this. In addition, we observe a sediment drape across the frontal ranges with conglomerates dated about 12 million years, draping up to about 600 meters altitude, which is over 300 meters above the present-day thrust front. How did these conglomerates get here? And how do we explain this draping feature? So Thomas Bernard used a numerical box model to simulate this situation in a flexural basin. He tracked 4 parameters: the range elevation, the basin elevation, the amount of sediment flux coming in from the origin into the basin, and the amount of sediment flux going out of the basin into an outer sink. He drew 4 cartoons to represent 4 key points in time. The end of convergence here at 23 million years, which is late orogenesis, when we have basically a standard system of orogenesis with sediment supply in red coming in from the origin. The flexure of the basin is ongoing, and we have a small amount of sediment exiting into the outer sink. About 3 million years later, we have no more flexure. The basin is starting to uplift. This is the isostatic rebound in the post-orogenic phase. We have less sediment coming in, but still a very high sediment supply from the origin, and an increasing amount of sediment going out into the outer sink. However, this high sediment supply causes the deposition of this sediment drape up over the thrust front. When we go to 15 million years, 5 million years later, everything is degrading. So the amount of sediment coming into the basin is degrading. The amount of sediment going out of the basin is increasing. We still have a sediment drape here, and we start getting very strong rebound in the total outer section of the Foreland system. And finally, in present day, we are in late post-orogenesis. We still have sediment coming in. We have got high uplift, and we are actually now eroding the Foreland Basin, and all the sediment is going out into the outer sink. Constraining time in the geological record is a major and ongoing challenge when we work in basins. We're constantly striving for higher resolution in age, time, duration, and rates of processes. The dating and correlation of non-marine or fossil-poor successions is particularly problematic. Stable carbon isotope profiling, calibrated with biostratigraphic studies, represents a powerful tool in these situations, particularly for the Cretaceous and Paleogene record. In her thesis and publications, Constance Vansiguera and her co-workers have used chemostratigraphic studies based on carbon isotopes to achieve high-resolution correlation dating of Upper Cretaceous and Paleocene Foreland Basin stratigraphic sections on both sides of the Pyrenean origin. Her work on the Tremp Basin series on the south side of the origin is shown here. Here, the Campanian and Paleocene successions consist of deltaic, shallow marine and fluvial sediments. Constance constructed the Delta C13 profile for her succession using terrestrial organic matter and marine fossils in a series of samples, calibrating the profile with existing magnetostratigraphic and sparse biostratigraphic data. She here correlates on the right-hand side the profile with the Delta C13 record of marine reference sections, which are shown here, with her own succession on the left. The coloured bars represent well-dated isotopic events. And you can see here that some of these events can be correlated across, suggesting that some of these unconformities, for example here, may be climatic in origin, while other unconformities may be tectonic in origin. So in summary of this section, we can say that early routing systems in the Pyrenean origin are axial and come from the east. We have a single early convergence basin controlled principally by post-drift thermal subsidence. We have to ask the question, are these early source areas to the east inherited, or did orogenesis initiate in the east and migrate to the west, which is what we think probably happened. The main collision phase is characterized by a growing origin that becomes the main sediment source, and therefore we have transverse drainage systems established and continuous through the Eocene, Oligocene and into the Miocene. The transition from early convergence to main collision can be detected in the stratigraphic record, where it is seen to occur from early Eocene onwards. However, we have to be careful when we're using the low temperature thermochronology record because we see a diachronaity in the exhumation history, and it indicates a maximum relief established at the end of the Eocene. So we see the beginning of growth in the stratigraphic record, we see the maximum relief in the low temperature thermochronology. The transition from synorogenic to post-orogenic is clear, has been detected by Thomas Bernard in his work on the North Pyrenean front, and he's shown that there is a clear sedimentation signal of draping across the thrust front, and that this transitional phase lasts about 18 million years. And finally, Constance's work has shown that a multi-method dating approach can provide new insights into higher resolution processes in our stratigraphic record. To conclude, I will make some very general statements. First of all, we have to remember that the Pyrenees is a low convergence origin that inverted a hot rift. It was a non-cylindrical origin that was highly segmented due to rift inheritance. However, based on all the results that I've presented to you here, we can say that we have now a better understanding of the onset of convergence and particularly of early orogenic processes. We have a better understanding of the transitions between major orogenic phases and their signals in different data sets. The role of inheritance in Foreland system evolution at different scales has been investigated and clarified. In particular, we now understand better the signals of the hot rift, of plate segmentation, of mechanical stratigraphy, in particular salt, and other factors. And we have an improved time resolution, which allows us to quantify rates of processes and distinguish reaction times in different data sets. And to close, I would like to thank Total, the BRGM and the CNRS for creating, funding, managing and animating the Orogen project. This was a fantastic opportunity and a fantastic project over the last 5 years, and I thank all my colleagues and our students for collaborating in this outstanding earth science project.